Welcome friends to this video on principle of electrical and electronics engineering. In last video we have seen what is a BJT. BJT stands for bipolar junction transistor. Then types of BJT, NPN and PNP transistor. Next its construction and then working. In this last video, we are going to see the various configuration of BJT. BJT can be configured in common emitter, common base and common collector. We are going to see one by one. First is common emitter configuration of BJT. Here our objective is to obtain the input and output characteristics of common emitter configuration. In common emitter configuration, emitter is common to collector and base. Here emitter is common to collector and base. You are having one voltage source which is VBE. On the right hand side you are having a voltage source that is VCE. You are having an ammeter which will give you IB. You are having an voltmeter which will give you VBE. Then you are having an ammeter which will give you IC. Then you are having voltmeter which will give you VC. Here our objective is to obtain input and output characteristics. Input and output characteristics. Input characteristics is obtained by varying VBE. VB is varied and the IB is noted down. This is your input parameter. In the circuit diagram, VBE is input and IB is input. EB is varied and for that corresponding IB is noted down. During this process, VC is constant. VC is constant. Now this graph is called as graph drawn between VBE and IB is called as input characteristics. Next one, output characteristics. Graph drawn between VCE and IC. Here VC is varied and for that variation corresponding IC is noted down. Here IB is kept as constant. For input characteristics, output voltage is kept as constant. For output characteristics, input current is kept as constant. This is called as output characteristics. Now let us get into the input and output characteristics of common emitter configuration. And here we are having an NPN diode, NPN BJT. Here we are having an NPN BJT. Here emitter base is forward bias and collector emitter is reverse bias. As here base to emitter is forward bias and collector to emitter is reverse bias. Now let us get into the characteristics. This is your input characteristics. Here you can see that a graph is drawn between VC and IB. Here VC is kept as constant. First is VC is kept as 0 and then VB is increased from 0 to 0.8 volt. Then corresponding IB is noted. Then VC is set a value which is greater than 0. Then again VB is varied from 0 to 0.8 volt. For that input corresponding IB is noted down. This is your input characteristics. Here what happens is when VC is 0, When VC is 0, EB is forward bias. Forward bias, and it behaves as a diode. It behaves as a diode, and hence for any change in input, the output increases. But when VC is set as greater than 0, what happens is the the width of the width of the depletion region at VCE increases, and hence you need higher VBE, and hence you need higher VBE to move the device into conduction, and hence the curve shift from left to right. When VC is greater than 0, the width of the VCE increases, and hence we need to apply higher VBE to turn on the device. This is your input characteristics. Next one is output characteristics. This is your output characteristics. Here it is having three regions. One is cutoff region. This region is called as cutoff region. Here both the junction are reverse bias. Here both junction reverse bias. There is no output. Next one is saturation. This region is called as saturation region. Here both region are forward bias. Here both region are forward bias. This is called as saturation region. This region is called as active region. In active region, emitter base is forward bias and collector base is reverse bias, and you can see that VC has no effect on your output. For any change in IB, IC changes. For any change in IB, IC changes. Here in this active region it is used as amplifier. In active region it is used as amplifier. In cutoff region it is used as switch. In cutoff region both are reverse bias. In saturation region both are forward bias. In active region EB is forward bias and CB is reverse bias. And you can see that for any change in input there is no effect on your output, but the output changes whenever there is a change in IB. The output changes whenever there is a change in IB. That means here amplification is happening, and hence BJT is used as amplifier in this region. BJT is used as amplifier in active region. This is your output characteristics. Next one is your CB configuration. In CB configuration, Here base is common. In CB configuration, base is common. On left hand side we are having voltage source which is VEB. On right hand side we are having voltage source which is VCB. This is your graph. On the left hand side we are having VEB. On the right hand side we are having VCB. And then you are having voltmeter which will give you VEB. You are having an ammeter which will give you IE. You are having a ammeter which will give you IC. You are having voltmeter which will give you VCB. Next one is input characteristics and output characteristics. Here input characteristics refers to a graph drawn between VEB and IE. A graph drawn between VEB and IE. Here VCB is constant. VEB is varied, and for that varied VEB, IE is noted down. Then if you draw the graph between VEB and IE, then it is called as input characteristics. During this process, VCB is constant. What is output characteristics? A graph drawn between VCB and IC. Graph drawn between VCB and IC is called as output characteristics. Here, IE is constant. Here, IE is constant. VCB is varied. For that varied VCB, IC is noted. A graph drawn between VCB and IC is called as output characteristic curve for CB configuration. This is the way to obtain your input and output characteristics curve for CB configuration. Now let us go into the curve. Now this is your input characteristics. It is drawn between VEB and IE. In this process, VCB is kept as 0. When VCB is kept as 0, what will happen is EB is forward bias. This emitter base junction is forward bias, and hence it will behave as a diode. It will behave as a diode, and for that, when the device turns on, for any change in input, the output will change. But when you increase VCB greater than 1, when we increase VCB greater than 1, what will happen is the base region width will decrease. The base region width will increase. The base region width will decrease, and hence you need lesser voltage to turn on the device. When VCB is greater than 1, the base region width will decrease. In previous characteristics, we have seen that there is an increase in the width, and hence the curve will shift right. Here, the width will decrease, and hence the curve will shift to left. This is your input characteristics. Then output characteristics. This is your output characteristics. Here you can see that a graph is drawn between VCB and IC. The graph is drawn between VCB and IC. Here, and then IE is varied, and then IE is varied from 0, 1 ampere, 2 ampere, 3 ampere, 4 ampere and 5 ampere. Here you can see that VCB has no effect on your output. Even though VCB is varied from 1 to 5, the output does not change. The output changes whenever there is a change in IE. The output changes whenever there is a change in IE. That is, IC is independent of IC is independent of IC is independent of VCB, as VEB is forward bias. As VEB is forward bias, the current IE, it enters into, or it gets collected by IC. As VEB is forward bias, the emitter current is collected by collector region and it is reflected at your output. Even though VCB is reverse bias, because of the polarity, IC changes. IC changes and it increases in value. This is your output characteristics in common base configuration. Next one is common collector configuration. Common collector configuration. Here collector is common. Here collector is common between emitter and base. On the right hand side you are having voltage source. It is connected between emitter and collector. On the left hand side you are having voltage source which connects base and collector. That is VBC. Here it is VEC. Here collector is common. Here the current is, the input current is IB. Here the output current is IE. What is input characteristics? A graph drawn between VCB and IB when VCE is constant. What is output characteristics? A graph drawn between VCE and IE when IB is constant. This is called as input and output characteristics curve for a common collector configuration. VC is kept as constant and then VCB is increased, and for the corresponding output is noted down, and then again VC is set to a different value, and then similarly VB is increased and IB is noted down. This is your input characteristics. Then output characteristics, it is very similar to your CE configuration. Output characteristics of CC is similar to CE configuration. It will have same active region, saturation region and cutoff region. In cutoff region, both junction will be reverse bias. In saturation region, both junction will be forward bias. In active region, one junction will be forward bias and another junction will be in reverse bias. This is your output characteristics for CC configuration. Next one is current amplification factor. What is current amplification factor? The ratio of change in output current versus the change in the input current. This ratio is called as current amplification factor. In CB configuration, the current amplification factor is DIC by IE. That is output by input. IC is output, IE is input. In CE configuration, the amplification factor is IC by IB. IC by IB, that is collector current is output, IB is input. In CC configuration, the amplification factor is IE by IB. IE is output, IB is input. This is called as current amplification factor in BJT. This is the end of your session. Thank you for watching this video.